Have to remind me of that every single time. Good thing I didn't start anything. Yeah, well, okay. Anyway, moving on, thank you. Right, so we're just going to be talking about a thing moving in one direction, not changing directions. And that should be fairly simple to understand, right? So whereas before, we might have to specify a velocity, meaning a speed and a direction, using a vector, because as we all know, vectors represent things with magnitudes and directions. In our simple case, when we're just working in one dimension, i.e. straight line motion, vectors are just positive and negative numbers. And the reason for that is because you can always just say, look, in our straight line motion, we're going to have, say, some velocity, 5 meters per second, in, say, for example, the j hat direction. But if it's straight line motion, there's nothing else happening in the I or the k direction. So all motion would be assumed to be in the j hat direction, and so you can kind of just drop the j hat, i.e. there's a one-to-one correspondence between positive and negative numbers and vectors in one dimension. That shouldn't be so surprising because the number line is a one-dimensional space, and you could have vectors on it, right? It is just the x-axis. You could have vectors like I hat, or 5 I hat, or minus 18 I hat. And so, but we don't do that. We just say 5 and minus 18 instead of keeping the I hat around. So everything that we're going to do is basically just going to be with positive and negative numbers here, because that's enough for one-dimensional motion. So first, let's talk about the simplest concept in motion. This is displacement, right? So motion is, from the standard dictionary definitions, it's basically just a change of position over a duration. And that should be fairly straightforward, I think. That's how we all agree with duration. And so the way that we describe this is we describe this position as a variable, say x, that changes with time. This is the coordinate position. Right, so your position is located somewhere on the x-axis. That position is called a coordinate position because a point on the x-axis has a coordinate, right? Just like how you might have coordinates in the xy plane. So we can also, so we can talk about a change in that coordinate. So a change in x of t is displacement. And again, this is just a standard dictionary definition. Displacement is just moving something from one place to another, right? So the displacement is defined as, often we'll write delta x, and we'll drop the t because this is a displacement from one point in time to another point in time. This is x final minus x initial. And you could also write this as x of t final minus x of t initial, right? It moves from point A to point B from the initial time to the final time, right? An important point to note is that if the final position is smaller, i.e. further to the left on the number line, than the initial position, then what we get is a negative displacement. And that's okay. This is not distance traveled, this is displacement. So a good example of this might be that a person walks forward 14 meters, then backward 5 meters, then forward 3 meters, and then backwards 20 meters. So you could ask the question, what is the total displacement? So we have plus 14 meters, then minus 5 meters, because backward on the number line means going to the left, negative, then plus 3 meters, and then minus 20 meters. So then the total displacement would just be the net change in position. So we can do the math here. We get that this is minus 8 meters displacement, or 8 meters to the left. Those are equivalent things. So this example is just to indicate a word of caution that displacement is not equal to the distance covered. Right, because the distance covered in the above example is 19, 22, 42 meters. Displacement is just final position minus initial position. So with displacement out of the way, displacement is the simplest concept, it shouldn't take long, we can talk about average velocity. So you guys all know about speed, and velocity is a generalization of that. So velocity is how we describe, or it is how one describes how fast motion is. That is, you can have two equal displacements, but if they take place over different durations, then one will have taken place faster than the other. Again, fairly intuitive things. If you drive to work, if you drive 20 miles to work at 10 miles an hour, it will take you more time than if you drive to work at 30 miles an hour, right? So we define this concept, average velocity, which we give the name v sub AVE for average, is just delta x over delta t, just divided by. These are all numbers, so you can just divide things as you normally would. And that is xf minus xi divided by tf minus ti. Remember that xf is really the x position at time tf. Xi is the x position at time ti. So in general, so stepping away from one-dimensional motion for a moment, in general, displacement is a vector because you could have maybe your displacement vector is 5 meters north, 3 meters east, for example. So what that says, because displacement is a vector, the average velocity has to be a vector. You can add and subtract vectors. So if x is a vector and if x is a vector and t is just a number, you can add and subtract vectors, and you can multiply and divide by numbers. So I would not use v. I would not use v with a bar on top for average velocity because that looks awful like the v vector. So I would use v sub AVE or v sub average. But we won't actually talk about average velocity a whole lot. But the point here is, just like displacement, velocity is a vector. And we'll have velocity vectors later on. Average velocity is vector. So another example, this one is just a little mind bender. If you walk forward, so let's say walk forward at 3 meters per second for 4 seconds, and then backward for 6 seconds at 2 meters per second, well, you might ask, what is the average velocity? So this is almost a trick question, because what you guys might want to do is you might want to say, well, you take some weighted average of 3 meters per second and minus 2 meters per second or whatever. But you're right, the average velocity is just 0. And the reason is because you just find the total displacement, divide it by the total duration, and you get the average velocity. And that's because delta x in this case is 0. Right? As you guys correctly guessed, you travel forward for 4 seconds at 3 meters per second, that's 12 meters. Then backwards for 6 seconds at 2 meters per second, that's minus 12 meters. So you get a total displacement of 0, which tells us that v average is 0. 0 meters per second, to be more precise, and the displacement should be 0 meters. Right. So average velocity is great, but it helps to cover this concept of instantaneous velocity as well, because that's a little bit more relevant in the real world. That's the kind of thing that your car displays when you're looking at the speedometer. So if we want to talk about velocity during motion, i.e. how fast are you moving while you're moving, this is at a single point in time. So the way that we handle this is we use calculus. So this is going to be our first use of calculus in this course. You take the limit of the average velocity as time goes to 0, or as the change in time goes to 0. So the instantaneous velocity is just, let me move this over a little bit so I have more room, is just v. It's the name that we give it is just regular v, and in the future when it's a vector, it'll be v with a little arrow over it, is the limit as delta t, yeah, sorry, that just, I guess, didn't take, is the limit as delta t goes to 0 of delta x divided by delta t. And this is just the derivative. It's dx dt, where x is a function of time. So keep in mind here that delta x is equal to x of ti plus delta t minus x of ti. And this should be fairly straightforward because delta t is the amount of time between ti and tf, and if you add ti to delta t, you'd get tf. So this is still just tf minus, or x of tf minus x of ti. So we can just keep going. We already talked about instantaneous velocity. Now we can talk about average and instantaneous acceleration. So the next thing that you might ask is, okay, so instantaneous velocity basically told us how quickly are you moving at any given instant in time. The acceleration tells you the change in velocity over time. That is, this is the idea, acceleration covers the idea of speeding up or slowing down. Later, when we get to multi-dimensional cases, or motion in 2 dimensions or 3 dimensions, it will acceleration will take on one additional meaning, but we'll get to that. So the average acceleration, and I know I'm just introducing a whole bunch of notation here, but we need to get it out of the way. This is a sub AVE. That is just delta V over delta T, which is VF minus VI over TF minus TI. Now, in this case, these V's, V sub F, V sub I, those are the instantaneous velocities at those times. So in order to find the average acceleration, you have to first know the instantaneous velocity at any given moment in time. The instantaneous acceleration is, we do the same thing as we did for the instantaneous velocity. The instantaneous acceleration is just given the name A for acceleration. And this is, again, just the limit as delta t goes to 0 of delta v over delta t. And again, this works out to be the time derivative of v as a function of t, right? Because if v is a time derivative of x, v is a function of t, right? It depends on time. So we can take the time derivative, and then this can be easily seen to be 2 time derivatives of the position. So just a word of caution for the language that you choose to use when speaking about or writing about acceleration. Acceleration is any change in velocity. It's not just speeding up, right? So often in common parlance, we'll talk about, oh, he's accelerating or he's decelerating. When we're talking about acceleration in physics, it refers to, you would say, oh, they're accelerating in this direction. If they're slowing down, that means accelerating in the opposite direction of the direction that they were moving, but they're still accelerating. It's always just acceleration. That's just the language we use. So just be careful there. Right. So I think we're making good time. so those are just all of the ideas that we have. So the question now is how do we actually use these concepts of displacement, velocity, and acceleration in order to talk about the actual motion of an object over time? So the way that we relate these concepts are by things called equations of motion. So equations of motion are literally just ways to fit x, v, and t, and x, v, a, and t together. These are also, what we're about to do is also called kinematics. So if you wanted to Google or look something up on Wikipedia, kinematics is probably the thing to look up. Specifically, we're doing one-dimensional kinematics. And by the way, at this point in time, we are not yet talking about causes of motion. Causes of motion are due to interactions, and we haven't even begun to cover how things interact with each other. We're just talking about things are moving, and they have such and such a motion, they move in such and such a way. How can we describe where it will be in the future? So typically, at least for now, we will deal with constant acceleration, meaning that the acceleration, even though it could be a function of time, we're assuming it's just a constant. It's just a number. That is, a being dv dt. Well, so if the acceleration is constant, we can do some things with this formula, right? The acceleration is defined to just be dv dt, right? That's just from this formula up here. That is what the acceleration is. But if the acceleration is constant, we can use this formula to find the velocity. Now, there's two ways we could go about doing this. One is we could just ask, look, what type of function has a constant derivative? Well, hopefully you guys all know that's a linear function. All linear functions have constant derivatives. And so we could just guess the formula. But we could do this a little bit more rigorously, more mathematically, by doing the same thing to both sides. So you know that you're always allowed to do the same thing to both sides. You know, that's just a standard algebra thing. So what we're going to do is we're going to integrate from 0 to t of both sides with respect to dt. So that's going to be equal to 0 to t of dv of t prime, dt prime, dt prime, right? All I'm doing is I'm doing the same thing to both sides. And then I'm going to apply the fundamental theorem of calculus to this side. This is the integral of the derivative. And this is just taking or integrating a constant function. So the left-hand side is just at. The right-hand side is v of t minus v of 0. And so we can rearrange this to get the velocity as a function of time is just linear. It's a times t plus v of 0. And we call v of 0 v naught from now on. So we now have a linear function with constant acceleration. And so this should not have been surprising, right? Any function that has a constant derivative, which the velocity function has to if the acceleration is constant, can be written as just the derivative times t plus some intercept. And we call that intercept v of 0 because that is the value of the velocity when t is 0. So we can do the same thing again for position. Or coordinate position, rather. So, sorry, just have to, my notes are falling apart. So we have that v is dx dt. And so again, we just integrate both sides. We have the integral from 0 to t of v of t prime times dt prime. By the way, I'm just making both sides functions of t prime, because it doesn't matter what we call the variable t. So I'm renaming it to be t prime, just so we can do an integral properly. And this is equal to the integral from 0 to t of dx of t prime dt prime dt prime, right? And we already know what v of t prime is. And so we can do the integral, right? We can plug that in, do an integral, and we're left with 1/2 a t squared plus v naught t is equal to, well, again, we use the fundamental theorem of calculus. What do we get? We get that this is x of t minus x of 0, and we're going to call x of 0, we're going to call it x naught. So again, we can rearrange, and we get x of t is equal to, it's equal to 1/2, actually, let me write it in the standard way, x naught plus v naught t plus 1/2 a t squared. And so here's our second kinematic equation. So here's our first, tells us velocity as a function of time, and our second tells us position as a function of time. And note that these formulas are only true when we have a constant acceleration. So the real question is what can show up in these equations? Like when would you use these types of equations, right? Well, in this case, t is the independent variable. So sometimes you might be asked to solve for t. In other cases, you'll be given t and you want to find something else. X of t and v of t are the dependent variables, as should not be surprising. And then there's constants. These are all quantities that show up. X naught, v naught, and a are constants of motion. So these are just properties of the motion that we're describing. Now, we assumed that a was constant. It didn't have to be, but then our calculation, or these formulas wouldn't apply. So in the case where these formulas apply, a has to be a constant. By the way, using these two equations, you can rearrange them in plenty of other ways to get useful results. I'll just give one example of a result that you might get. Basically just rearranging them and solving them for other things. So one such equation is 2 times a times xf minus xi equals vf squared minus vi squared. So basically what I did is I took t, I substituted in tf, and then I subtracted from that x, or I took x and substituted in tf, and then I subtracted from that x when I substituted in ti. And then I looked up to what that's equal to. I substituted that back into here and did some algebra to it. But there's nothing spooky going on here. This is just another useful kinematic equation that comes from these first two. And there are a lot more. In particular, by the way, this particular equation eliminates the time dependence from the above equations, right? So this is now just tells you how the velocity is related to the displacement and the acceleration. It doesn't care at all about time. You can also, for example, compute v average. V average is just v naught plus vf over 2. This is v average at some, or from t equals 0 to t equals tf. And there's a whole lot more. Right. So that takes us it's not through to the end. We still have quite a bit more to cover today. But I would like to open the chat up for maybe a minute or two just to get any quick questions out of the way about kinematics. So does anybody have any questions? So that's a good question. It's just to avoid this problem that a lot of people will end up doing. You don't have to do this, but it's just a math thing. You don't want to be integrating the same thing that is in your bounds as is your variable of integration. So I just use t prime because it's technically correct, but it doesn't actually matter, right? You just want to avoid that. So I called it. Yeah, they're the same thing. So I just called it, because t in this case is just a dummy variable, right? You're integrating over it, so it doesn't matter what you called it. I could have called it q if I had wanted to. No. So you will. So I was just explaining where these formulas come from. I probably won't. You guys should know how to do this, but I can't imagine I will be testing on this. T prime so there's context here. T prime, there's nothing to take the derivative with respect to t2, so we're not. So when I write t prime in this context, that does not refer to the derivative of t. Maybe I just shouldn't have used that and just abused the notation, because that seems to be adding to the confusion rather than subtracting from it. You can just imagine that I had removed that all of these t primes are actually t's, and nothing will be different. There. Now, hopefully it's less confusing now. You can, but t final is often assumed to be like a constant rather than a variable that you can change at will. So that's why I use t. You don't have to be following the LibreText physics book while watching lecture. Like it's completely up to you how you want to do it. You know, it's just a study question, I suppose. This is material that you will need for the last homework problem. Yeah. So now we're actually I'm gonna cut questions short because I do want to continue. So we're gonna talk about free fall. So free fall is basically what we're going to be, will be useful for, if I have time, I will get to an example, yes. But I mean, you know, you guys have all taken algebra, you're all competent enough with, you know, moving symbols around, so does it matter if I call it A as opposed to 5? Anyway, so first, before we continue, I'm going to actually show you a video about free fall. So let me share screen. This one, share computer sound, share. So hopefully you guys can all see this. This is a recording from one of the moon landings. I'm just going to show you a little bit. Hopefully you have your sound on.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Right, so just a quick little video, but the point hopefully was made clear that things fall at the same rate, regardless of what they are, assuming that there's no air resistance and all of that business, which we often have to worry about. The whole purpose of that is to illustrate that when things are falling, they undergo constant acceleration. So let me just write out some words. Free fall on the surface of the planet, on the surface of a planet or moon, on the surface of something large and gravitational, is constant acceleration downwards. It undergoes motion that has constant acceleration. And by downwards, I just mean towards the surface of the planet. Or moon. And the purpose of showing that video is just to illustrate that, yes, in fact, everything does have the same constant acceleration because they hit the ground at the same time. They must be moving at the same rate. So it turns out on Earth, not one, on Earth, I can never decide whether or not to capitalize the E in Earth or not. That acceleration, that constant acceleration, is typically called g. And g represents the number 10 meters per second squared, approximately. It's 9.806 or something, but 10 is good enough. And often we will refer to the vector g would be 10 meters per second downward. So the magnitude of the vector g is just 10 meters per second. So you'll often see people write mg for the without the vector on top of it, and so that g is just in place of 10 meters per second squared. So when I say that something accelerates in some direction at 5 g's, yes, you guys should be using 10. I don't want to see too many decimals. It just makes it harder to grade. When I say something accelerates at 10 g's, that means that it's moving at 100 meters per second squared, or it's accelerating at 100 meters per second squared in whatever direction I specified. G's don't always have to be downwards. It's just a handy unit for acceleration, because we can relate it to everyday experience. Hell, if you guys really want to, you can use pi squared meters per second squared for g. That would be fine too. I really don't care. Just use something that's easy to see and doesn't clutter up the calculation too much, which is why I prefer 10. Right. So under free fall, if something is falling with no nothing causing that motion besides just gravity, we would just say that the acceleration might be minus g, because perhaps you say downwards is in the negative direction and upwards is in the positive direction. Now, you could have also chosen it to be plus g, so downwards is positive and upwards is negative, but then you just have to be consistent with how you're choosing your coordinate system. Something I wasn't very particular about in the last sections, or the last lectures, that I should be more clear about here is that before you do any problem, it's useful to actually define what your coordinate system is, so that just that way then you're consistent, because otherwise you might end up adding things that should have been subtracted and so on. So that's just a useful tip. If at the beginning of every problem you say, and every problem that needs it, you say, let plus x be, or let the plus x direction be up, let the minus x direction be down, and the left be minus y, or whatever, just for consistency. All right, so the last thing to cover for today is graphing. So this is graphing motion, really. And this is just useful because it's a good way to get visual understanding of what's happening. So it turns out it is useful to graph x of t and v of t. And so some goals that you might, or some reasons you might want to graph things is to satisfy these goals. It's to, for example, you could interpret graphs in terms of physical motion. You could, if you were given some motion, you might be asked to sketch a graph. Some word description of motion. You also might be asked to sketch a graph of x of t given the velocity, or vice versa. And these would be in terms of like actual formulas, like v of t is 5t minus 3 or something. Then you'd be asked to sketch what x of t looks like. So for the first of these, you might be expected to try to understand the following graph. So let's say that you have a graph that looks like this. So here we have x, here we have t. Let's say your graph looks like first like this, and then there's something happens, and then it goes like this, curves and levels out, and then it goes like this. Let's say your graph looks like that. So what I would expect you to do, given this graph, or to interpret from this graph, is something like, where is the object? I might ask you, on what side of the origin is the object at such and such a time. Now you would look here and you would say, hey, at all times, the x value is positive. At all times greater than t equals 0, the x value is positive, which would mean that the position, or that the object is to the right of the origin for all times for positive t. I might also ask you, is the object at rest or is it moving? How would you tell that? Well, think about what it means for an object to be at rest. It means that its position is not changing with time. So there are only two times when its position is not changing. That would be here and here, right? Its velocity is 0 because the slope of the graph is 0 at those points. And when the velocity is 0, so is the object is at rest. At all other times, the object is moving. Its position is changing. You might also ask, what direction is it moving in? How do you find that out? Well, you would look, is its x position, its coordinate position, increasing or decreasing? In this region, for example, its coordinate position is increasing for every point in time, right? But in this area, its position is decreasing. So in this case, it's moving left. However, over here, it's moving right again because its x position is increasing. And increasing x, we've already defined. So plus x equals right. I should have specified that beforehand. Another question that I might ask, is it speeding up or slowing down or neither at some particular point in time? Now, hopefully, if I drew this properly in, let me erase these little circles and erase that. These are all just example of things I might ask you. Yeah, okay, Brianna, that's a good point. You're right, the derivative doesn't exist there. You could take you could say that the object infinitesimally approaches being stationary on the left side there, but in general, you'll never have discontinuous derivatives for motion in the real world. So not actually a thing to worry about. But good question. Right, so the last thing that I could ask is it speeding up or slowing down? So you might say in this region, from t equals 0 to say t equals t1, it's doing neither. It's a constant velocity. In this region, it's slowing down, i.e. the speed that it had, which is represented by its slope, effectively, the magnitude of its slope, is decreasing. It's going from, it's going fairly quickly, and then its position is changing less and less as a function of time. So here, it is slowing down. Now, this is where it gets tricky. In that region, the velocity is negative because it's going from right to left. Its position is going down. But the magnitude of the velocity is going closer and closer to 0. So in this case, we would say it's slowing down, but it's accelerating in the positive direction because its velocity, which was negative, is becoming closer to 0, i.e. more positive. Or acceleration to the right, one might say. And then in this region, it should be fairly clear that the object is both speeding up and its acceleration is to the left, or is to the right. So those are the types of questions that I might ask when I say, interpret this graph, right? These are all types of things that hopefully you guys have seen this type of thing in pre-calculus, like analyzing the slope, analyzing whether doing like the second derivative test to figure out whether it's concave up or concave down. All of those things can be translated into physics language, right? Positive slope means positive velocity. Negative slope, negative velocity. Concave up, positive acceleration, i.e. acceleration to the right. Concave down, acceleration to the left, i.e. negative acceleration, and so on. Why does the slowing down part has acceleration to the right? Right, okay, so that's the trickiest one to grasp here, and I will spend some more time on it. Good question. And And Matthew, yes, even though the graph is slowing down, it is still moving to the right in this region. Just think of it as a car coming to a halt, right? It's slowing down, like pressing on its brakes, but it's still moving as it does so. But to get back to Cherry's question, so it's slowing down in that its speed is getting closer to 0. Note that speed is like the absolute value of velocity, or the magnitude of velocity. So its speed is getting closer to 0, but think of it like this. If you're on a number line, if initially the speed is, or the velocity is this vector, and then later on the velocity is this vector, and then later on still the velocity is this vector, you can see that that the change is acceleration to the right, i.e. if you take this vector and add a little bit of that vector, you get this vector. If you take this vector and add a little bit more, you get this vector, and so on. So it's accelerating to the right, i.e. positive acceleration, because its velocity was negative and it's getting closer and closer to being positive. Its velocity was to the left, but it's getting closer and closer to being to the right. So this is this issue, and it's common, is a result of understanding, is a result of not thinking of acceleration as meanings, or thinking that acceleration is the opposite of slowing down. Yes, you can tell by seeing if xt is concave up. Yeah. All right. So the second thing in these goals was to sketch a graph given a description of motion. So in order to do that, you might have to say, I might say, let's say that a ball starts off with some speed and then rolls up a hill. So it starts off on the ground with some speed, and then it rolls up a hill. So it initially has to have a non-zero slope because it has some non-zero speed, and then it rolls up. So what happens to its velocity as it goes up the hill? Its velocity should go down until it gets to the top of the hill, and then maybe the acceleration instantaneously changes because now it's at the top of the hill. So let's say that this is top of hill. And now its position will go down. Well, okay, perhaps this is a bad example because that's actually two-dimensional motion. Let's say instead an object is thrown upwards, right, with some initial speed. So if it's thrown upwards, what would that look like? It has some initial speed, but its initial height is 0. It's thrown upwards, but the speed decreases linearly. And so it'll reach the top of its arc at some point in time. And then it'll reverse direction and continue to fall. And so what you can see here is that this is a parabola, by the way, is that even though the position is positive at all times, its velocity changes direction because the slope goes from positive to negative. And similarly, the acceleration is always downwards the acceleration is always negative or downwards because it's concave down. And you can tell that by looking at how the slope changes. The slope is initially rather high, and then it gets less steep, and then it increases in the opposite direction. Another tool that you'll need is to be able to graphically integrate. So to be able to graphically integrate, what that means is just, it means that you should be able to guess what the integral or what the position looks like as a function of time given the velocity. And it's really not that hard once you get the idea of it. It's just know that linear functions become quadratic, constant functions become linear, and so on. So for example, say I gave you v of t as a function of time. And let's say the velocity function looks like this. Then in order to graphically integrate that to get the position as a function of time, I would say, look, here we have a parabola, so it should be constantly increasing there up until that point in time. And then the slope is constant after that. So here we have a linear function. And then you just stitch the answers together because the motion is continuous. And then similarly, you could also graphically differentiate, just plot the derivative as a function of time. And here you'll find that this is actually not constant motion, not constant acceleration motion. Here the acceleration is positive because the slope here is positive up until you get to this point in time, and then the slope becomes 0. So these are tools. Being able to go back and forth from the different graphs is very useful because it allows you to visualize more what's going on given either the acceleration or velocity position. So let's go back to the ball rolling over a hill example. I'm just going to plot the x, or the vertical position. Actually, no, this is a hard example. Yeah, I'll just plot well, it'll look exactly like this, basically, if you were just looking at the vertical position. So I'm actually not going to give that example there. The most straightforward examples, though, and really the most complicated example that you're going to see in one-dimensional motion is just constant acceleration, or maybe acceleration that changes piecewise but is constant otherwise. And it'll just be crazy things like the example that I gave up here, right? We have constant acceleration here. This is a parabola, not parallel. Parabola. This is linear. And then here we have another parabola. Now, the thing that happened is that the acceleration changed values between these points, but it's still constant in all 3 of these cases. So we still know how to handle it using the kinematic equations that we have. So I'll open it up for questions now. We have about 2 minutes left, and then we'll have those informal office hours at the end. But that'll take us through to the end of the material I wanted to cover today. I know it was fast, but so for that I apologize, but we do what we have to. I don't have the discussion videos. You'll have to ask the TAs if he has them. I didn't particularly tell him to record them because it's not, again, yeah, it's not mandatory. So I'm not, like, if you guys all send him emails though asking him to record him, he probably will. But you know, that's up to him. Sunny, you have a question about the homework. The coefficients in front of G. Sunny, one moment. So let me answer Kayla's question first. So when you say the coefficients, you mean like 5G? So, right, okay, thank you for the clarification. So when I say 2G, just think of G as literally meaning 10 meters per second squared. So if I say 2G, that means 20 meters per second squared. And 3G means 30 meters per second squared, and so on and so forth. That's all I mean. Pavel, so for kinematics, the way you phrase that question makes me very much not like that question, because it makes me think that you just want to just plug and chug into equations without actually knowing what they're used for. So in general, I'm not, and you know, I'm sure that's not the case, but that's the impression that I've gotten from a lot of students in the past. In general, I'm not going to tell you which equation to use. You're going to have to know what the equations mean to see which equations are appropriate for a given question. I will be asking you, hey, this thing is undergoing this type of motion. What is its position at time 5 seconds after it started, for example? That's kind of what the last question is on the homework is like. So the last question is just an application of the kinematic equations, but you just have to know how to apply them appropriately. My understanding is that one of the TAs is holding more office hours today. I can double check, but I believe that's true. You don't have to be able to derive them. You just have to know what they mean. Like, I mean, it's not hard to derive them. It's just doing 2 integrals. But if you know what they mean, that should be good enough. Like what each term represents and why it represents that, and so on and so forth. Just looking today, there are additional office hours today. Or no, there were office hours before discussion or before lecture. So G is so when I write G, the number without a vector, it's just 10. 10 meters per second squared. You can leave things in terms of g. That's fine. Well, it's fine to leave things in terms of g until the very end, where if you're asked to find a number, then you should probably calculate. Sunny, you did have a question about the homework, though, and I want to get to that question. So what was your question?
Hi. So I had a question on 4A.
Yes.
The question was, how high above the surface of the Earth does the rocket travel before it stops accelerating? So do you mean when it stops accelerating at 2g, or stops accelerating?
Yes, when it stops accelerating at 2g. Yes,
Okay.
That's a good clarifying question. Lucas, you will not need to memorize equations. I will give. So my general rule of thumb is if an equation has 4 symbols or has more than 4 symbols in it. Yeah, if an equation has more than 4 symbols in it, then you don't need to memorize it. If it has 4 or fewer symbols, then you do. And that has some wiggle room. Like some very fundamental equations have 5 symbols, so those you should memorize too. But like, for example, later we'll see F equals ma. That has 4 symbols, so you should memorize that one. But I'm not going to expect you to memorize, you know, the kinematic equations, because those are a bit much, and I'd rather have you understanding what they mean than having them memorized. That said, often I will not give you. Oh, I'm going to stop recording because we're done with lecture.